Our next speaker is Ted Innamorato from UNC. Thank you, Ted.
Is it working now? Perfect. Hi, everyone. Thank you all for being here. So today I'm going to be, is it showing? How do I do this?
It should be on full screen mode.
There you go. Well, my name is Ted Innamorato. I'm an assistant professor in political science at UNC Chapel Hill. And today I'm going to be talking about my work on how to bring together information from multiple sources in fast and accurate ways. So to illustrate how important this is for us in the social sciences, let me walk you through a question in my discipline, political science, that has attracted the attention of many scholars and for which bringing together information from two datasets, not working with one dataset at a time, is going to play quite an important role. So here in red, I have plotted the actual turnout rate among the voting eligible population of the United States for the past 5 presidential election years. It has fluctuated between 52 and 60 percentage points. Then in red, I have plotted the turnout rate you would obtain if you use the responses of the participants of the American National Election Studies, ANES, one of the most prestigious, if not the most prestigious public opinion survey there is in this country. As you can see, there is a large gap throughout these past 5 electoral cycles from what people self-report and the actual turnout rate in the population. The puzzling thing here is that the ANES spends considerable amount of time and efforts into trying to target individuals from the population of interest there, like the voting eligible population. So the question becomes, what drives this gap? So there are two competing theories. Some authors claim that it's all about over-reporting, people claiming that they voted while in fact they did not, as a result of social desirability bias. They want to appear to be good citizens. There is another stand that, or a set of authors that said, like, it's not about over-reporting. What is happening here is that these surveys, the people that are more likely to answer these surveys are people that are more likely to vote to begin with. So while you are targeting the voting eligible population of the United States, what you end up with is a biased sample of likely voters. To understand if it is either over-reporting or having a sample of likely voters, what is that we have to do? Well, we have to find these survey respondents in a voter file and try to contrast their self-reported behavior with their actual behavior. How is that we're going to do that? We will have to merge the datasets. But this is going to be a tricky merge because we are not going to have access to the social security number of every respondent of the ANES, and we don't have the social security number of every individual in the voter file. So we'll have to use the information in common between the datasets, names, addresses, zip codes, to try to conduct the merge. The problem there is that we don't know whom is whom in this dataset, so we'll have to make a guess. The big question is how we're going to do that. A standard approach is to use deterministic methods. So we're going to propose a set of rules on how we are going to declare pairs of records to be matches and non-matches. The most likely approach is to use exact matching. For every pair of records, we're going to check if they have the exact same values in the variables in common between the datasets. Why is that approach so appealing? Because we're going to be really conservative in what that we declare to be a match. The problem is that there are topographical errors in the variables in common or missing values, then we're going to start declaring as non-matches pairs of records that refer to the same individual. And this has real-world consequences. For the past election in the state of Georgia, 50,000 records were put on hold because their information in their voter registration record did not match the information in their social security card or in the license. This can be the result of a missing hyphen or a typo in the license, for example. And what happened here is that this was like a sort of like, it was portrayed as a history of disenfranchisement because this was targeted like the people that are more susceptible to have this type of errors in the names. And the addresses were racial minorities, Hispanics, and African Americans. Another popular approach is to use proprietary methods. We're going to contact a company like Catalyst YouGov. They're going to conduct the merge for us. This has the main advantage that we just sit down, relax, and then we receive a merged dataset. But in the sake of transparency, we don't know like the steps that this company take in order to declare a pair of records to be a match or not. And they tend to be quite expensive. A more popular approach among statisticians and computer scientists is to use probabilistic models. Since the very early models, these models were designed to control for the two types of mistakes that we can make when we declare a pair of records to be a match or a non-match: false positives and false negatives. However, appealing that idea might sound, like there are a couple of challenges with standard approaches of probabilistic record linkage. The first one is that open source implementations do not scale. What do I mean by that? As our datasets become larger and larger, it takes more time and computational resources to conduct these merges. And then the second problem is that after you have conducted a merge, as a good social scientist, what you do is try to do like random spot checking, check here and there if the merge was conducted correctly. Then you learn some information. Then you learn perhaps that the model is trying to control the false positive rate as less than 1 percentage point, but you find more than 1 percentage point worth of false positive. So you have learned some information. How can you incorporate that information into standard approaches of probabilistic record linkage? We don't have that. To solve these issues in terms of scalability, in joint work with Ben Fifield, now at Facebook, and Koski Mai, now at Harvard, we have proposed FastLink, which is a series of algorithms on how to scale the standard approach of probabilistic record linkage. And then in terms of accuracy, how can we incorporate our human judgment into the merging process, I propose the use of active learning. So this is how the rest of the talk is going to look like. First, I'm going to talk about the standard approach of probabilistic record linkage. Then I'm going to walk you through how I incorporated the standard approach within an active learning framework. And then I'm going to show you results from the question that I started this conversation with. What drives the large gap between self-reported and an actual turnout? Not to keep you in suspense, we will learn that it's mostly about over-reporting. But I have to convince you that that's the case. So the Fellegi-Sunter model. So this is a model. First, let's think about like what is the standard workflow that we have in mind when we merge datasets. Well, we have two datasets. We have the variables in common. We need to make comparisons across the values that these variables in common take. Then we're going to feed those comparisons to our classifier, which is going to be the probabilistic model. And then the classifier is going to let us distinguish if a pair of records is a match versus a non-match. So some common notation before I go through. Like first, I'm going to talk about how we make comparisons. How we make comparisons, so we're going to have two datasets. These datasets, they need to have variables in common. And to make the comparisons, we're going to make use of this function that is called an agreement value. So we're going to take a pair of records, and for every variable in common in that pair of records, we're going to compare the values according to some similarity measure. So for strings, we can use Levenstein, or we can use another measure that is called Yarrow-Winkler, that the only difference is that they do a character-wise comparison of two strings, and Yarrow-Winkler, for example, gives more weight to the beginning of a string. And then for numeric variables, we can use the L1 norm, the L2 norm. And then we have to discretize the comparison. Why the discretization is because we are going to gain a lot of efficiency in terms of computational time by making these comparisons discrete, while like we're not going to be sacrificing too much in terms of precision. Then when we have made these comparisons for a pair of records, like the ones that I have here, we're going to have this object, an agreement pattern, which is for every pair of records, we're going to have a history of similarity levels across these variables in common. So in this case, we know that this process is robust to, for example, typographical errors, where a Smith there is just missing one letter H. But as you can imagine, this is a really difficult task, because like if you have two datasets of 1,000 observations each, you don't know whom is a match to whom. You have to make 1 million comparisons per variable in common. So if you have 6 variables in common, you have to make 6 million comparisons. To show you how difficult that is, there are like two mature one R package and one Python library, both called record linkage. In the case of record linkage R, to merge two datasets of 50,000 records each with 6 variables in common, it takes 22 hours to conduct that merge. Then this is when I started working on this problem, that I said, like, that's too much. Then it's like, is there any way that we can improve upon that running time? Then by using hashing and representing hashing as in a form of sparse matrices, We here are gonna make use of sparse matrices because like they are like we know that they are really efficient objects to store data. And not only that, most of the comparisons that we make are disagreements. So like if we compare two names, the most likely outcome is that they are gonna be different. And that's a way that we don't need to keep track of those disagreements by using a sparse matrix. We are gonna just store the comparisons that are different from being that they are likely similar or identical. And in that case, to merge two datasets of 50,000 records each, instead of spending 22 hours, we only spend a couple of minutes. And this grows linear in time. Now the Fellegi-Sunter model. So the Fellegi-Sunter model, we're gonna feed these comparisons, these agreement patterns. That's the only data that we observe, and we're gonna feed that into this probabilistic model. The data that we don't observe but we wish to observe are these unobserved matching status, this latent variable, match, not match. We don't observe that, but what the Fellegi-Sunter model does, it models that. So we're gonna model the matching status as if it comes from a Bernoulli distribution, where the parameter lambda is gonna tell us like, it's gonna try to approximate the rate of true matches between the data sets, and then every pair of records represented as an agreement pattern is gonna be allowed to come from the set of matches and the set of non-matches. So we can have a pair of records that have agree on almost every variable in every field and can have a probability of 0.99 of being a match, but by random chance, it could be the case that these individuals have the very same variables in common, and then we're gonna allow it to have a probability of 0.01 to be in the set of non-matches. The parameters of the model are recovered using the expectation maximization algorithm. Well, one thing is to improve upon like implementation and scalability. The other problem is like, what about accuracy? And what happens with the Fellegi-Sunter model, and like this is a common critique to this approach, is that the model thinks that using the parameter of the model, you think that you're controlling the false positive rate in less than 1 percentage point. But what happens in practice, once you have conducted a clerical review, you have checked these cases, then you learn that actually the model is making many more mistakes than it's supposed to. Like in this case, 7 percentage points. So like there is a wide gap. And that is gonna have real consequences when you do post-merge analysis, because you think that you're controlling the error rates, but this can mean that you are not matching certain type of observations. And if those type of observations, let's say like African American or Hispanics are your target population, then you're gonna start making more mistakes there. So how are we gonna fix the mistakes? And this is where I said like, let's incorporate active learning into this framework. The idea here is that imagine that we have piles and piles of unlabeled data. What if we were to observe some labeled cases? Actually, Larsen and Rubin and Winkler, they have shown that if you mix labeled and unlabeled data, then you can improve in terms of controlling the error rates. But there are two challenges with this type of approaches. The first one is where is that we're going to obtain labeled data to begin with. We have piles on piles of unlabeled data when we're merging two datasets because we don't have a unique identifier. What are the best cases for us to inform the model so that it learns the most in terms of classification? So that's an issue. The second one is, imagine that you have two datasets of 1,000 records each. You have to make 1 million comparisons. And you say like, well, I'm gonna help the model too, and I'm gonna label 50 cases. Still you have more than 900,000 pairs of records that are unlabeled and only 50 cases that are unlabeled, they are labeled. How is that in a maximum likelihood framework, you're gonna make the model to learn more with this unlabeled data? Because if not, the likelihood is gonna be just guided. The parameters of the model are gonna converge every time if you weight the data the same to the same set of parameters, because the model is gonna be just informed by the unlabeled data. And in that case, to solve the first issue, what are the most informative cases, I propose the use of active learning in record linkage. And basically, it's this iterative process where we're gonna interact with the Fellegi-Sunter model, and we're gonna ask the Fellegi-Sunter at each iteration. Fellegi-Sunter model, where is that you're having problems with in terms of classifying pairs of records as matches and non-matches. But because we started in a world where we only have unlabeled data, let's feed the Fellegi-Sunter model as a first approximation. Then we need to select cases to be labeled. So let's say like, if we ask the Fellegi-Sunter model, where do you have problems with? the Fellegi-Sunter model is going to be quite greedy, and it's going to tell us, like, I have problems with these 10,000 cases, and you cannot do that. Like, it's a lot of time that you can spend, and a lot of you need a lot of human power to try to classify, to do hand labeling for 10,000 cases. So like what we're going to do is we're going to select as researchers the number of cases. So let's say that you tell to a Fellegi-Sunter model, I'm going to help you with 40 cases. So how is that we're going to select those 40 cases? Basically, we're going to use uncertainty sampling. So we're going to select the cases where the Fellegi-Sunter model is basically flipping a coin first, but we're going to sample as a batch. So we're going to also sample cases by virtue of random sampling, cases where the model thinks that it's making no mistakes, just to double check that it's doing a good job. Then we have sampled these 40 cases. Then we say, like, well, now we need to do the annotation. How is the annotation process going to come through? So we're going to be presented the information in common between the data sets. And then we have to make a call. Is this pair of records a match or a not match? And then here, here's where our human judgment can be really helpful to the Fellegi-Sunter model. The Fellegi-Sunter model is allocating a probability of 0.6 for this pair of records to be a match. And what is driving that probability to be 0.6 is that the place of birth is different in this case. It's widely different. But we know something. We know that Princeton, New Jersey, this small beautiful town in New Jersey, is located in Mercer County. Once we know that, then we know that the remaining information is basically the same. We can make the uneducated guess to say that this pair of records corresponds to the same individual. This also has the advantage that it informs you that maybe, there is, you should take a step back and try to fix the problem with the place of birth. So that's another bonus of trying to use this type of supervision in the Fellegi-Sunter framework. Then we need to feed a model using labeled and unlabeled data. But as I mentioned before, if you only have 40 cases that are labeled and you have millions of cases that are unlabeled, how is that you're going to inform the model so that it learns more from this labeled data? So here, I followed a literature in text classification that basically tells you that you can take combine labeled data and unlabeled data, but sort of upweight the contribution to the likelihood of you can penalize the contribution of the likelihood of the unlabeled data. So we're going to use this parameter of mega. The model is basically the same. For the labeled cases, the matching status is fixed, but the models are connected because the rest of the parameters are the same across types of data. And then we're going to use the parameter omega that is going to go from 0 and 1 to say how confident we are in the. Basically, by saying that omega is really small, we're going to upweight the importance of the labeled cases. And then we're going to repeat this process until the classification that we get from one iteration to the other, it doesn't change much. So let me walk you through, again, what drives the gap between self-reported and actual turnout. And to remind you of the causes, so we are thinking about over-reporting or having a sample of likely voters. So those are the two competing theories. What was the merge? Through a cooperative agreement with the ANES, I had access to all the identifiers for the ANES, so the names, the addresses of the survey respondents of the ANES. And then for 2016, that's 4,300 respondents. And then at Princeton, we had access to the border file from L2, which is a commercial vendor of border files. That border file for 2017 has more than 180 million records. So the merge, how is that we conducted the merge? The information in common are going to be the names. That basically for the ANES, we extracted, these are good quality names, but because we extracted them they paid them with every respondent with a check. So we used the names in the checks. And we parse those into first, middle, and last name. Then the ANES sampled based on addresses, so the addresses were quite clean. And then we also have a measure of age. In terms of the blocking scheme, so we need to reduce the number of comparisons because if you compare data set that has 4,300 respondents with 180 million records, you're going to be making trillions of comparisons. So to reduce the number of comparisons, I conducted this merge in 2 stages. So I subsetted the data by state and gender. That leaves me 2 groups. That gives me 102 subsets per subsets, and I conducted a merge there. So that's what we call a within-state merge. So we actually allowing people to either move within the state or remain in the same place of residence. But we know that in this country, individuals move at really high rates. So to allow for individuals for the possibility to have moved from the time that they were measured in the border file and in the survey, I conducted a merge for all of those individuals in the ANES that I couldn't find in the first pass. I looked for them everywhere in the country. So that's the across-state merge. So this is the gap that I started that was in the other plot. Just for 2016, there was a 17 percentage point gap between what people self-reported in the actual turnout rate in the population. If you use the Fellegi-Sunter model and then you don't label any information, and you take the model as a good approximation of the truth, then what you get is that now using the information that we have gathered from the border file, instead of self-reported turnout, you get that the individual, like the respondents of the ANES, as recorded in the border file, they voted at a 66 percentage point rate. So there is here, this tells us that mostly 11% of the gap, 11 percentage points of the gap can be attributed to overreporting. These individuals, they were claiming that they voted while in fact they didn't. But then around 6 percentage points can be attributed to having a bias sample. So, but this, I showed this when I was doing this. I had to go and spend 10 days at Stanford doing this. When I was doing this, I go to the leaders of the ANES and I showed this result, and they were like, "Oh, that but our sampling scheme is as best as good as you can get. We don't think that we have a bias sample in that amount. So can you do something to check that your model is not making wrong predictions?" And then I said well, in the interest of science, I'm gonna go after this. So I said what is the reasonable thing to do? Because I was young and naive at the moment, and I said I'm gonna, for every respondent of the ANES, I'm gonna hand code the best set of matches and see if the model was making mistakes or not. Maybe I was missing some individuals, or maybe I was misclassifying and saying that they were a match, but in fact they were not. Because the turnout question is only asked in the post-selection component of the survey, that involved for me to do this for 3,600 respondents, one at a time. So this was me, the very first day in beautiful Palo Alto, working on this, and the very first day is in the interest of science, let's keep pushing this. The second day is what did I get myself into? The third day was, no, I cannot keep doing this. It's 20 hours a day working on this. And then the fourth day was there has to be a better way. And actually there is. If you use active learning and embed this Fellegi-Sunter model, you get the very same answer that you would have obtained using a thorough clerical review. But the point here is that the conclusion is different. Most of the gap can be attributed to overreporting. So the model was making some mistakes, classifying the individuals within the same household as possible matches, but actually they were not. And then once you have a good measure of overreporting, then you can try to see what correlates well with overreporting. And what we found is that the more educated, the wealthier, interested in politics, and more partisan an individual is, the more likely that person is going to be to overreport, which goes along to stories of social disability bias. These individuals are the ones that want to appear to be good citizens. So to conclude, if you don't have a unique identifier, probabilistic models offer us a really general solution to this problem. There are fantastic work being produced here at Duke. Rebecca Storrs is working on ways on how to reduce the number of comparisons in really smart ways, proposing more generative models. Jerry Reitner is also working on how to work with de-identify information, because once we have conduct a merge, we want to protect the identity of our matches. So that's another big problem. And people like me and Mauricio Sadinle, who was a postdoc here, but now is at University of Washington, we're working on trying to make the measures that we use to compare names, more robust to the fact that some typographical errors are more likely to occur for different type of races, like Hispanic names, African American names. And then what I showed today is by incorporating human judgment into the merging process, we can take this really simple model, the Fellegi-Sunter model, and try to improve its accuracy. And then all these functions that implement the active learning approach are going to be made part of the R package that we have released a couple of years ago, FastLink. Thank you.
Okay, yeah. Okay. So let's get some questions going, and then in about 3 minutes, we'll ask the next speaker to come and set up.
So I hear some bits of the questions. So,
I'll talk loud.
so
I
you
wonder if you've looked at other data sets to see if the proportion of reporting versus bias sample apply to other data sets.
So when I conducted this, I did it for 2 surveys. I did it for the ANES, and I did for another survey that is called the Cooperative Congressional Election Studies, which is conducted online throughout. But there, it was a more challenging merge, and because the fields are measured with error, everything is self-reported, and these people are not being paid much. So the information is not at highest quality. So there are 2 challenges there. It is true, you can have a bias sample. That's still I think that's a more problematic thing for that type of surveys. And the other is it's really difficult to disentangle because the quality of the fields, probabilistic record linkage relies on having, there can be error in the fields, but up to a certain extent. There is a place where that can be also a challenging thing. But of course, there are gonna be type of surveys where this can be an issue. So right now, what the Fellegi-Sunter model does is, so the question was is there any way to weight variables differently within this framework? And that's a good question. The Fellegi-Sunter model, what it's doing is trying to use the discriminatory power of every variable to try to come up with a weight. And actually, there are variables like age. So the probability of being a match is just a summary statistic of all these, of these weights. And basically, the Fellegi-Sunter model does a good job to tell a variable the year of birth doesn't do much power, doesn't have too much discriminatory power, because think about it. The probability that the 2 individuals were born in the very same year at random is really high. So that is one of the advantages. And then what we don't have now is good approaches to say what are good variables to do the merge and what are good variables to, maybe they don't have too much discriminatory power, but they can help you reduce the number of comparisons. So comparing only individuals that were born around the same year of birth. So that's something that I have been playing around a little bit, but I think it's a good point. So right now, what we use are for names, we usually use the Yarrow-Winkler string distance. As I mentioned before, gives more weight to the beginning of a word, and this comes from work in linguistics that have shown that people tend to make more mistakes on the second part of a string. For addresses, what I use usually is the Levenshtein distance, because with addresses, I don't have a clear intuition if there is going to be a typographical error in the beginning or in the end. But the problematic thing here is that so probabilistic record linkage is going to be better to the extent that we spend more time in parsing the data. But we can only parse the data up to a certain point. At some point, we have to start doing the merge. And then my idea with this type of approach is that we can go and see actually how the merge is, how the probabilistic model is classifying pairs of records, and try maybe to learn from those mistakes. And then if the county is a problem because like it was in one case it was a county and in the another case it was a town, then we can go back and try to fix the data and then maybe like get better results.
Okay, great. Thank you very much. So let's thank our speaker again.